So now we will look how we will represent the real numbers on the number line. So the process of visualization of representation of numbers on the number line through a magnifying glass is referred as the process of successive magnification. So here we will use the process of successive magnification to locate or visualize a number on the number line. See, so here let's take an example of locate the number 2.664 on the number line. So here the given number is the terminating number. So we know that this digit 2.664 will lie between 2 and 3. So here we will say this number will be somewhere between 2 to 3. So suppose we divide this number into this line between this line 2 and 3 into 10 equal parts and mark each point of the division as shown in this figure 1. So to have a clear view, we may take a magnifying glass and look at the portion between 2 and 3. See, let's take a magnifying glass and look between this number. So here we say this is number 2 and this is number 3, and we have divided this number into 10 equal parts. So like 2.1, 2.2, 2.3, 2.4. So now we can clearly see between the digits between 2 and 3. So now again we will look into the given number that 2.664. It will lie somewhere between 2.6 and 2.7. So again we will take this portion between 2.6 and 2.7, again divide this number into 10 equal parts. So and taking the magnifying glass, so we will look uh, into this region. So this will become as shown in figure 3. It will be look like this. So here, and this digit is like 2.7. So we have divided it into 10 equal parts. It become like 2.61. It will become like 2.61, 2.62, 2.63, 2.64, 2.65, 2.66, 67, 68, 69. So now we will look that this digit will be somewhere between 2.66 and 2.67. If we look into this digit again, so 2.664, so this will be like between 2.66 and 2.67 and will be closer to the 2.67. So here we can look like somewhere between 2.66 and 67, so somewhere between this point. So again we will divide this into 10 equal parts and taking a magnifying glass, so it will look like the figure 4 shown in figure 4. 66 and 67, so somewhere between this point. So again we will divide this into 10 equal parts and taking a magnifying glass, so it will look like the figure 4 shown in figure 4. we have divided this line into 10 equal parts, it becomes 2.661, 62, 663, 664, 5, 666, 667, 668, 669. So here we can say that 2.664 is this point. In this way, by using the successive magnification or by using the magnifying glass, we can clearly locate the given number by reducing the length of the number line. Look into how we apply the operations on real numbers. So we know that real numbers are the combination of both rational and irrational numbers. And we also know that the rational and irrational numbers satisfy the commutative, associative, and distributive laws for addition and multiplication. So what are these laws? As commutative laws are like a plus b is equal to the b plus a, or a into b is equal to the b times of a. And what is the associative law? So we can say like a plus b plus c will equal to the a plus b plus c. And similarly for multiplication, like a into b into c is equal to the a into b into c. And the distributive law is the combination of multiplication and addition law. So like a times of b plus c equal to the a times b plus a times c. So these are the laws. These are the two laws, and we know that these both rational and irrational numbers follow and satisfy these laws. Now, if we add, subtract, multiply, or divide, except any zero, two rational numbers, we still get a rational number. Means if we perform any operations like we add, subtract, multiply, or divide, except zero, two rational numbers, so we will get again rational numbers. Similarly, the sum, difference, quotients, and products of irrational numbers are not always rational numbers. They may be rational or they may be irrational, but the sum, subtraction, product, and division of rational numbers is always the rational number. So, and if we add or subtract two rational and irrational numbers, then the number will be always be irrational numbers. So next, like if we perform the operations like addition, subtraction, multiplication, and division on one is rational number and another is irrational numbers, so then we will always get an irrational number. So we can say like when we add, subtract, multiply or divide two rational numbers, so we will always get a rational number. But we perform the same when we perform the same application on the irrational numbers, so we are not sure that we will get the rational numbers. We may get rational or we may get the irrational numbers, right? And when we perform these four operations on the rational and irrational number together, so then we will always get an irrational number. So let's see how we perform the operations. Whether 7 is square root of 5, 7y square root of 5, square root of 2 plus 21, 5 minus 2 are irrational numbers or not. So we have to check all these numbers whether these are irrational numbers or not. So let's see. So let's take. So we know what is the value of square root of 2. So the value of square root of 2 is 1.4142 and so on. The value of square root of 5 will be like 2.236 and the value of pi will be like 3.1415. So now check. Now let's take first value, that is the 7 times square root of 5. So, so here we can say we have a one rational number and another irrational number. So the product of the rational and irrational number will always be an irrational number. So let's check. So here 7 into value of square root of 5 is 2.236. It will be like 15.65 and 2 and so on. So here we can say this value is non-terminating and non-recurring. So this is an irrational number. Second one is 7 by square root of 5. If we multiply the square root of 5 on both sides, that the numerator and denominator, so we will get like 7 times of square root of 5 upon square root of 5 into square root of 5. So we will get 7 times square root of 5 by divided by 5. So here we can say we have got this rational number 7 by 5 into square root of 5 a rational number. So again the multiplication of rational and irrational, we will get an irrational number. So when we will perform this the operation on this, so we will get like 3.1304 and so on. So again this one is the non-terminating, non-recurring decimal expansion. Again, this is an irrational number. So now let's look on to the third expression, that is square root of 2 plus 21. That is equal to the given square root is 1.4142 plus 21 equals to the 22.4142 and so on. Again, non-terminating, non-recurring. Again, this is an irrational number since uh, the remainder or quotient is not terminating and it is also not recurring, right? So next one is like pi minus 2. Again, value of pi is 3.1415 and so on, and minus of 2, so we will get like 1.1415 and so on. Again, the value is non-terminating and non-recurring. So again, this value is given, the number is the irrational numbers. Now, so we know now if we want to take the square root of real numbers, what we will get. So let's say like operation of taking square roots of real numbers. See, we already know that if a is a natural number, then we can say square root of a is equal to the b. Means, what does it mean? It means a equal to the b square and b is always greater than 0. So the same definition can be extended for positive real numbers. So we can say let a is greater than 0 be a real number, then square root of a is equal to the b. Means a equal to the p square and p is always greater than 0. So similarly, we can calculate the nth root of the real number. Now we have to define the nth root for a real number, where a is greater than 0 and n is a positive integer. Let a is greater than 0 be a real number and n be a positive integer. Then we can say nth root of a is equal to the p only when if b to the power n is equal to the a and b is always greater than 0. In this way, we can calculate any root of a given real number. So here now we need to remember some identities, some formulas that will help you in solving the numericals. So there are some identities. So we are given two numbers. Suppose let a and b be positive real numbers. Then first identity is square root of a b is equal to the square root of separate of both numbers, that is square root of a into square root of b. Second identity is square root of a divided by b. We can write it again square root of a upon square root of b. Next one is square root of a plus square root of b times square root of a minus square root of b is equals to the a minus b. Next identity is a plus square root of b times of a minus square root of b. It will becomes like a square minus b. Next is like a square root of a plus square root of b times of square root of c plus square root of d. Then that will becomes like ac plus square root of ad plus square root of bc plus square root of bt. And next one is square root of a plus square root of b the whole square, and it will becomes like a plus 2 times of square root of ab plus b. So these are the some identities that we need to remember, and we will apply this in the following examples. Simplifying the following expressions. So first is 5 plus square root of 7 times of 2 plus square root of 5. what will be the solution? So here we can clearly see that square root of a plus square root of b times of square root of c into square root of t. By applying this identity, we will get what is that identity, like square root of a plus square root of b times of square root of c plus square root of t. So what we will get? We will get square root of ac plus square root of AT plus square root of BC plus square root of AT. So here we will get here A equal to the 5, A equal to the 5 square, B equal to the 7, C equal to the 2 square and D equal to the 5. So here we will get A into C. So we will multiply this 5 into 2. It becomes 5 into 2 plus 5 into square root of 5 plus square root of 7 into 2 plus square root of 7 into square root of 5. So here we will get 5 to the 10 plus 5 square root of 5 plus 2 square root of 7 2 times of plus square root of 35. So this will be the simplification. So now we will take the next problem, like 5 plus square root of 5 times of 5 minus square root of 5. So here we will apply the identity a plus square root of b times of a minus square root of b, and it will becomes like a square minus b. So here applying the identity in this formula, here a equal to the 5, b equal to the 5, right? So we will become like a square 5 square minus square root of 5 square. So it will become like 25 minus 5 equal to the 20. Here next is we will apply the identity square root of a plus square root of b ka whole square, and this becomes a plus 2 times of the square root of ab plus b. So applying this identity here, a equal to the 3 and b equal to the 7, so applying the same identity will become 3 plus 2 times of 3 into 7 plus 7. So 7 plus 3 becomes 10 plus 2 times of square root of 20. So next one is like square root of 11 minus square root of 7 times square root of 11 plus square root of 7. So here first we can apply the law of commutative law. Commutative law, what does commutative law says? It says like a times b equal to the b times a. So here we can say also write it like square root of 11 plus square root of 7 times of square root of 11 minus square root of 7. So now again applying the identity square root of a plus square root of b times of square root of a minus square root of b will become a minus b, where a equal to the 11 and b equal to the 7, so becomes 11 minus 7, that is equal to the 4. Rationalize the denominator of expression 1 by square root of 2. So what does mean here? What does mean by rationalization? So here the rationalization means an equivalent expression in which the denominator is a rational number. So we have to convert, we need to convert this denominator into a rational number. So here if we multiply the square root of 2, if we multiply and divide the square root of 2 on the given equations, it will become like 1 upon square root of 2 multiply the square root of 2 divide square root of 2, it will become square root of 2, right? So now here in the denominator there is an rational number, right? So in this form, so we can say in this form it is easy to locate 1 by square root of 2 on the number line, and it is halfway between 0 and square root of